So these problems are the ones that I identified as ones that were missed most frequently. This does not capture all of the information that you need to retain, but it is worth going over these. And I think the main thing with all this is kind of thinking more about the concepts rather than just here's how you find the specific answer. So in this case right here, the concept that we're talking about is what's the difference between a variable and a summary statistic. All right, because what we have is data collected on 35 students in a college history course. A variable is going to be a piece of information related to each case, each data point in the data set. So you could have, of course, when you've got your student, like student A, B, C, D, and whatever, they're going to have a birth month, they're going to have a political affiliation, their age, and their address. The number of students in the data set, that's a summary statistic. That's just a count of the total number of data points. So that is not a variable for each individual. That is just an overall summary of the data. So that is not a variable. So of course, that's going to be our answer right here. There we go. So this next one, this is a question, well, we can see right here. We've got electrical workers and concrete workers, and is this their salary? Oh, the number. Oh, it's just the number of workers. Okay, so it's kind of good to know what the context is here. So we've got the summary statistics, the 5-number summary specifically, and what we want to figure out is which of these following statements is a correct comparison. So now let's actually see what we're comparing. All of these are related to outliers. So really, we just need to figure out where the outliers are. And I'm only going to look at one of these. So I'm going to look at the concrete workers. And remember, to find the outliers, we use this 1.5 times the interquartile range. Well, your IQR is just your third quartile minus the first quartile. And so in this case, I'm only going to do concrete workers. I'm not going through the entire problem here. So your third quartile is 308, your first is 262. And when you subtract, you're going to get 46. All right, so now 1.5 times the IQR is going to be 1.5 times 46, which is going to be, if you do that math, it should be 69. So now what we're going to do is we want to figure out if we have upper, lower, or no outliers. And as a reminder, if you've got your box plot showing your 5-number summary, anything, so your 1.5 times your interquartile range, there's your interquartile range, so 1.5 would probably push my lower fence to about right here, I don't know. So if I had a data point down here, that would be considered an outlier. But I want to figure out mathematically exactly what those values are. Okay, so for this, I'm going to take the third quartile and add the 1.5 times the interquartile range. So that's 308 plus 69 gives me 377. Now I want to do the lower fence, which is going to be 262. That's Q1 right here, minus 1.5 times the interquartile range, which gives me 193. Now those values on their own don't mean anything, but what it tells me is that any value higher than 377 is an outlier. And that the maximum for concrete workers is 335. There's nothing higher than 377. There are no higher outliers. So the 193 is the lower fence. Anything lower than that value is an outlier. And I do have 186 is lower than that. So I am going to have a lower outlier. So I know for concrete workers, there's a low outlier. So I'm going to look through my answer choices and eliminate some possibilities. Both of these have high outliers for A. Well, that's not true. Both of them have lower outliers. That could be true. Neither concrete nor electric distribution has outliers. Well, I know that concrete does. Concrete distribution has at least one lower outlier, and I don't know anything about electrical, so I'm just going to leave the concrete as is. That one's plausible. And the last one is the concrete distribution has one high outlier, electrical has no high outliers. Concrete doesn't have a high outlier. So only B and D are the options. To narrow that down, I would look at the distribution for electrical, but I'm not going to do that right now. I think the key concept and takeaway, because it's not so much about this specific question, but it's remembering how to implement the 1.5 times the interquartile range rule in order to find your outliers. So good to see that again. The next one goes into the empirical rule. So in the Dominican Republic in August, the distribution of daily high temperatures is approximately normal with a mean high of 86 degrees Fahrenheit. Approximately 95% of all daily high temperatures are between 83 and 89 degrees Fahrenheit. What's the standard deviation? All right, so the first thing I want to remind you of, and some of you I hope are like immediately knowing what to do with this, but when you see this 95%, that should remind you of your empirical rule, the 68, 95, 99.7 rule, which tells me that within 2 standard deviations, I'm gonna have 95% of the data. If they had said 68%, that would be one standard deviation away from the mean. So now I want to kind of think of this as a normal distribution. I've got my mean right here, which is 86. And I'm identifying that right here, the mean of 86 degrees Fahrenheit. I know that 2 standard deviations away captures 95% of the data, and that's between 83 and 89. So somewhere about right here and here are 83 and 89, which means I have my other standard deviation in between about right here, which is going to be whatever's in between. Between 83 and 86, I've got 84.5, and then I've got 87.5 right here. So of course, none of those are my answer. What is the answer is what's the difference between these two, between any two, and that's 1.5. So my standard deviation is B, 1.5 degrees Fahrenheit. Right, and hopefully that is making sense for you. I think just as a key concept for all of this, especially those of you doing the AP test, but even those of you not who are just going to be studying for the tests in class, don't look at these problems as though like, I know how to solve this problem, I'm good to go. I want you to always kind of step back and look and say, I understand not only the question, but I understand the concepts underlying the question, because I'm not going to see this exact question again. But I understand the concepts that led me to this answer. So that's going to help you when you see a different problem that asks you something different, but you still have to use the same concept of the empirical rule and the normal distribution and things like that. All right. So the distribution of the number of moths captured per night by a certain moth trap is approximately normal with a mean of 103. So maybe I'll just stop right here because I know they don't just throw these numbers out. So the mean of 103. If 28% of the captures fall below 76 per night, which of the following equations can be used to find sigma, the standard deviation of the distribution? Now, the concept here is that we are talking about z-score, a z-score calculation, because it's talking about this 28%, that's the area under the curve. We've got sigma as part of it, which is what we're solving for. So what I want to keep in mind is that all of these are related to a z-score. And the z-score calculation is x minus your mean divided by the standard deviation. And now we need to kind of go through and figure out what's going on. The one thing I do know is that the mean is 103, so I'm going to go ahead and fill that in. And it looks like my data point of interest, it gives me another number right here. 28% fall below 76/9. This is going to be my X right here. So I'm going to put the 76 right here. So we're off to a good start. And what might be tempting is to say, oh, I got 28%. That 0.28 goes right here. And then, oh, I'll just find that answer. It looks like in this case, it would be B, except keep in mind, this is the mistake they expect you to make. And keep in mind that the area under the curve is not the z-score. That's the area that falls below your z-score. So what I want to do is I want to figure out what z-score corresponds to this 28%. All right. So what z-score is that? That gives me 0.28 as an area. And this is an inverse norm calculation. So it is 0.28 from the bottom, and this is where you have to be careful, read it. It says 28% of the captures fall below. So I know it's the lower 28%. So with a standardized normal model like this, that would be my calculation. And what I get when I do that is negative 0.583. So with that, I now know that my z-score of interest is negative 0.58. That's what the answer choice is given as. So even with just this z-score right here, I could cross out these three. And then of course I just need to look at the other side and realize that D is the answer. Again, let me just show it one more time. Kind of the key concepts is the z-score, understanding how to go from the area under the curve to your z-score. And there could be just so many different combinations of these concepts to give you all kinds of different questions. And you've seen a lot already. So kind of walk away understanding what you're being assessed on. Okay. So this, we're looking at a two-way table. And what happened was they got some violinists who were looking at violins and trying to categorize them. Some of the violins were old, some of them were new, and they were trying to categorize them as old or new based on their, what they think is their expertise. So here's the result. It was a new violin, and it was correctly identified as new. That was 15 times out of 33. It was an old violin, and they incorrectly classified it, so that's 13 out of 31. Or of course, maybe it was incorrectly classified, so what's the probability that it was new? 18 out of 31. So it's conditional probability is what we're going to be looking at, and that's the theme of this question. And remember, these are all questions that were missed by, in every case, a majority of people missed it, and these were the most missed problems. All right, so which of the following statements is supported by the results? The proportion of all new violins that are correctly classified is equal to the proportion of all old violins that are correctly classified. So we're looking for equality, and we need to see what our condition is. Proportion of all new violins, so it has to be new violins that are correctly classified, that's going to be 15 out of 33, is equal to the proportion of all old violins that are correctly classified. All right. That's going to be 18 out of 31 because the condition is that they're old. 15 out of 33 is not equal to 18 out of 31. All right, so that one is not true. Proportion of all new violins that are incorrectly classified. All right, so now this is good to draw on the two-way table as you're doing this. I know you don't have it in front of you, but you can kind of follow along with what I'm doing here. The proportion of all new violins, so I'm looking at new violins, that are incorrectly classified, so that's 18 out of 31, or 33, sorry, is equal to the proportion of all old violins that are correctly classified. Old violins correctly classified is 18 out of 31. Very close, but it's not the same proportion. So again, that one's not true. The next one, and I'll do it faster now. Proportion of all incorrectly classified violins that are old, 13 out of 31, is equal to the proportion of all correctly classified violins that are new. So that's 15 out of 33. Again, it's going to be close, but not the same proportion. All right. So the next one, the proportion of all incorrectly classified violins that are new, 18 out of 31, is equal to the proportion of all correctly classified violins that are new, 15 out of 33. Again, not new, or not correct. Those proportions are not equivalent. So it better be this last one or else we made a mistake. Spoilers, it's the last one. All right, the proportion of all correctly classified violins that are old. Correctly classified violins that are old is 18 out of 33, is equal to the proportion of all new violins that are incorrectly classified. New violins is the condition that are incorrectly classified, that's 18 out of 33. Now, I know I went through this somewhat fast, and you might need to really take some time to figure out, this is the condition, this is the probability. This is the condition, this is the probability. But as you work through it, it kind of just becomes rinse and repeat. You're doing the same thing over until you finally find a proportion that's the same. And here we found it. Okay. So E would be the answer. This one, we are looking at scatter plot data and correlation. So this is specifically the computer output if you're using a statistical program. And I just want to reinforce that the reason you're looking at this is because when you get to college level and it's not even necessarily a statistics class, you will have to do some statistical analysis in some of your college classes, and you will use a computer program to do it almost certainly. And it's going to give you something like this. So you're not going to be sitting there with your TI-84 doing least squares regression. Okay, so what we need to keep in mind, well, let's read the kind of the prompt, the stem here. So the ERA in baseball, ERA and WHIP are two statistics to measure the quality of pitchers. For both measures, a smaller value indicates higher quality. The following output gives the results from predicting ERA by using WHIP in a least squares regression for the 2017 baseball season. So we are predicting ERA from WHIP. So now I always try to encourage you guys to just draw a quick diagram here. The explanatory variable goes in the x-axis, and that is WHIP. And the response variable goes over here. So what's being predicted is ERA from WHIP. So now we want to interpret this 6.8, figure out what that means. So this is referring to our line, and what we have is the y-intercept, which is given right here where it says intercept. We're not asked about the -5, we're asked about this 6.8, and that represents the slope of the line. So for every one that we go over in the x direction, you're changing x, changing y, if you go back to algebra 1, well, my change in x here, if I just go over 1 in WHIP, it looks like I'm going to be going up 6.8. And it would, if it was negative, it would show it was negative, but this is a positive 6.8. So for every one change in WHIP, then we would predict a 6.8 increase in ERA. So ERA is predicted to increase by 6.8 units for each 1 unit increase of WHIP. There's the answer. I'm not going to read through all the other ones, but you can read that all those are not going to be describing what's going on. Okay. So I think the takeaway as far as just concepts on that one is just be, this is a very applied question. I mean, a lot of these are. But we want to be thinking about what is being predicted, what's being the explanatory variable here, and being careful to read this output, knowing that that's going to be something that shows up, almost guaranteed. then you want to make sure that you're comfortable with this. And they're always going to give you either the word constant or intercept right here to show you which one your intercept is, to show the actual value. We don't care about these others over here. So we only are looking at the specific values there. All right, a sample of students will be selected from all students at a high school. Which of the following sampling methods is least likely to produce a representative sample of the students? All right, so here's what well, you know what we're looking for, but let's go through this real quick. We've got the first one. From a list of all student names, randomly select 50 names from the list for the sample. Is this one representative? I'll go ahead and answer this one. Is this one representative? Well, it seems like it's a random selection of 50 from all student names. Yeah, that seems like it could be representative. All right, so just a couple things to talk about. All student names, this is your sampling frame. So that represents your population, or the group of participants that you could draw from the population, I guess is maybe a better way of talking about it. But we could kind of say that this is basically the population. And what kind of sample is this? Can anyone give a name to that?
Random.
It is random. And this is more specifically what we call the simple random sample, SRS. You could almost just pick a random number generator, 1 to 1,000, or however many are on the name, or on the list, and then just pick 50. All right, simple random sample. Next one, randomly choose 5 classrooms in the school and use all the students in those classrooms for the sample. What kind of sample is this?
Would that be cluster?
You got it. So that's a cluster sample. And because you're using all the school and all the students, those both seem like they'd be representative. So those are not the right answer. Divide the students into the 4 class years and randomly select students from each year in proportion to the number of students in each year. So what kind of sample is this?
Stratified.
Yay, stratified, good job. It's a stratified random sample. All right, and it should be representative. So we'll call that good. Remember, it's all the students included. From a numbered list of all student names, randomly choose a starting point and then choose every 10th student on the list. Anyone know what that's called?
Systematic sample.
You got it. All right, we're almost done. We're not going through, I don't even remember. But anyways, all student names. So that should be representative. So the last one, this better be the right answer. From a randomly chosen home basketball game, choose every 10th student who enters a gym. Well, we're not selecting every student, or the sampling frame that we're picking from here is not the same as the population. It's only those who went to a home basketball game. So that's the big problem here. So this is least likely to be representative. So there's your answer. Let me see, are we doing more? No, that's actually where we're stopping for the day. We'll start with this next problem. What the plan is, well, I'll go through that in just a minute.